I am Mr. Taru. In this video, we are going to do a nice thorough introduction of the basic geometric structure or figure of an angle. And through this discussion, we're going to be talking about the structure of an angle, which is what we're going to start here. We're going to be talking about how to name angles based off of their size. That's here. We're going to be talking about the protractor postulate, and as well as I can on the board, give you an idea of how to use a protractor and read measurements from it. We're going to be talking about the angle addition postulate, the idea or define what congruent angles are, define adjacent angles. We have an example of adjacent angles here, even though I'm not going to reference the actual definition of that until near the end of the video, and define what an angle bisector is. We're not going to be constructing that using a compass, just defining that concept for you. So let's get started, because we have a lot to cover. Angles. Well, angles, and I'll be using this sort of what looks like an angle with a sort of arc through the corner of it. That's the way I draw my symbol for angles instead of writing the word out, because if I don't include this arc, like some textbooks don't, I end up writing what effectively looks like an L, and it can be confusing. So this is going to be my math symbol that we use for angles. So angles are formed by two rays that have the same endpoint. Now remember, a ray is not in a complete line. Lines extend in both directions forever. It's not a segment that stops at it has endpoints, has two endpoints, whereas a ray only has one endpoint. And you can almost think of it as an initial point where the ray emits or originates from, like say a ray of light. Well, it starts with the sun, so that sun would be the initial source of the ray emanating from it. So, but we're calling it endpoint. So these rays have a common endpoint. I'd probably be saying initial point as well, because that's a vocab used in some other math books for other math classes, so just kind of interchanging that. So we have point B, we have an initial point or an end point of B, whatever you want to call it, and then the ray extends in one direction from there, and each of those two rays form the two sides of your angle. That common point for the rays, the common end point, the common initial point, we're going to identify that sharp bend there as the vertex. And then we have a little 1 marked in here in the corner of the angle. If you have especially if they're single digit numbers, the diagram is probably giving you an alternative way of talking about or naming that angle. If you have a little circle in the upper right hand corner of that number, though, that's indicating the number of degrees that angle is open. Angles, start kind of closed, if you will. You can think of it that way, and then start to open it up. That amount of opening is the number of degrees that the angle is sort of encompassing or has been opened up. So we have two rays, we have a vertex, those are making up the sides. Let's talk about how to name an angle. Well, in geometry, with very, very basic diagrams like this, you have many options of how you would like to name that angle. We can use 3 letters, and most of the time we name angles in geometry, because our diagrams that we're going to use are going to be a bit more complicated than this. You will need 3 letters to identify an angle. You're going to have a point on one side of the angle, or on one ray, a point on the other ray or side, and the center letter is, or variable, or point, it has to be the vertex. So we can call this angle ABC, keeping the vertex as the second letter, or you can go in the reverse order, that's okay. We can call this CBA, either one of those would be acceptable names for this angle. What would be incorrect, though, would be to say, to name this as angle CAB, because once you get used to identifying angles or naming them, you'll understand that center letter does need to be the vertex. So when you say angle CAB, well, that would be a completely different angle than what I have diagrammed up here on the board, so that would be incorrect. Keep that vertex as your second letter. If you only have one angle emanating from a common point or a point, if you only have that vertex, with one angle coming off of it, you can name an angle with just simply that vertex, the variable of that vertex. We can call this angle B, or we can use that inside number and just call it angle 1. We got another diagram here. These are adjacent angles. We're going to define what adjacent angles mean in a few minutes. I just want to talk, but I'm still talking about how do you name angles. When you have a vertex with how many angles do you see leaving from this vertex of H, by the way? Do you see 2 or do you see 3? Either way, that's a problem with using this very simple one-letter idea of naming an angle. See, you actually have three angles coming off of this vertex of H. You have angle DHF, which I don't have written up here in my notes, but sort of like the overall very large angle. And then this, you could think of this angle of DHF as being split up into two equal parts, DHE. So we have angle DHE, you can reverse the letters as well, just keep H in the middle. Or because I have that 1 in the corner of the angle, I can call it angle 1 as well. And then we have angle EHF, or angle 2, because I have that 2 marked in my diagram. What would be incorrect, probably should have done this in orange, is because I have a more complex diagram now, I cannot use this simple idea of naming the angle as saying angle H, because, well, angle H, what do you mean, the big one, or this top one up here, the bottom one down here? I don't know. So this now is going to be an appropriate name for that diagram, which is just a little bit more complex than my original one, but yet that simple version is no longer any good. And again, HEF, what's the problem with this name? E, which is the center letter or variable in my name, is not a vertex, so that would also be incorrect, and that's why. Okay, acute angles. Acute angles measure any kind of angle that is less or between 0 and 90 degrees. Now, what is 90 degrees? I don't have a protractor in my hand, but I do have a piece of paper. The corner of your paper is a 90-degree angle. This is square. Well, the entire sheet of paper is a rectangle, but we would say that corner, you could say that corner is square. That corner is a right angle. So when you're looking at your textbook or a test that you're doing or your homework, whatever, you can actually just use the corner of your paper, and let's just do that now. If I take the corner of my paper and I put the corner of my paper on vertex B, do you see how the other side goes underneath the sheet of paper? Well, that means that angle ABC, opens up less than 90 degrees. So this is an acute angle. It's between 0 and 90 degrees. An angle which is 0 degrees is just shut. And then it opens up and it opens up until it gets to about 90 degrees, and then it'll continue to open up and so on. If you have an angle that's exactly 90 degrees, that's going to be called a right angle. We're going to be talking about right angles a lot, because say if you're building a house, you want all the walls to have right angles so it's not leaning over and have a tendency to fall over. Right angles are going to help us create right triangles, and right triangles are a massive part of the study of a upper level math called trigonometry, which is extremely important for, again, building and navigation, and so it has tons of applications. So we're going to have you might go in college and have a semester course called trigonometry, or a high school course called trigonometry, and it is almost completely the study of right triangles that are made up, of course, that one main angle of a right angle. Obtuse angles measure between 90 and 180 degrees. So we have 0, we have 90, anything in between is acute. Once you get past 90, between 90 and 180 degrees is called an obtuse angle. Over here, a straight angle, if I take my arms and just kind of, open them up completely, and you think of my arms as the sides of an angle, if that's going straight, if it's 180 degrees, just a straight shot like a straight line, if your angle looks like a line, then it is a straight angle. Protractor postulate. On line AB, we're going to do a diagram to go along with this. But on line AB in a given plane, choose any point O between A and B. Consider OA and OB and all rays that can be drawn from O on one side of AB. These rays can be paired with real numbers from 0 to 180 degrees in such a way that OA is paired with this any value between with 0 and OB with 180 degrees. If OP is paired with X and OQ, with ray OP is paired with X and OQ with Y, ray OQ with Y, then measure of angle POQ is equal to the absolute value of X minus Y. Makes total sense, right? Maybe I should have stopped and included the diagram before I started reading it, because this all sounds like a bunch of gobbledygook. That's why so many people have trouble reading textbooks, but it does mean something. So let's take a pause, erase the left-hand side of the board, give you a diagram, and revisit this again and make it make sense. So here we have our protractor drawn. That's this yellow semicircle type diagram here. When you buy these at the store, a protractor has a straight ruler on the bottom, and there's usually like a little hole there where you're going to line up with this point O. I'm going to describe again here in a second. And then sort of like a half circle, a semicircle, that we're going to use to measure the measure angles that have measurements between 0 and 180 degrees. So again, let's look at that math language. It's supposed to tell us how to use a protractor. This postulate. On line AB, so that's what I have here, again a line because there's double arrows here. In a given plane, choose any point O between A and B. So I've marked this green dot point between points A and B, or on this line AB. Between A and B. Consider OA, ray OA, so the one directional mark here. Consider ray OA and ray OB and all other rays that can be drawn from O on one side of line AB. We're going to be measuring angles, and angles are made up of two rays. That's why they're making this point here in the definition that we now have taken this line and created sort of, two rays from it originating from point O. So we have that, so we can use that definition of an angle with our, protractor postulate. And we're only going to be considering all other rays, and I have three others drawn here. I have ray OC, OD, and OE, all drawn on that same side of line AB, because this protractor is only going to allow us to measure angles between 0 and 180. So they all need to be on one side. These rays can be paired up with real numbers from 0 degrees to 180. So the protractor postulate, a protractor allows you to measure the number of degrees that an angle opens up in such a way that OA is paired with 0 degrees and OB is paired up with 180 degrees. So basically what you're going to do is you'll have an angle drawn. So I can kind of cover all this up, maybe just focus on this ray OA and OC. So you would put the protractor down on that angle, and you put the protractor so that the hole in the protractor is going to be over point O, the vertex, and you're going to line up ray OA so that that side of the angle goes through. There's going to be a whole bunch of little numbers as you go around these arcs, and you want OA to line up exactly with vertex here at the hole on the protractor, and then going through 0 degrees. And then as you see the angle, let's say AOC, sort of open up, you're going to look at what tick mark, what angle degree measurement the other ray of the angle goes through. So we have one side going through OA, going through 0 degrees. You look at the other ray that makes up the angle and you see, okay, it's lining on top of 130. You might also notice that it's lining up with 150 degrees. A lot of protractors will have numbers going both this way and this way. If you have one of those, you want to make sure that, AOC is clearly acute. It's smaller than the corner of a piece of paper, and so you want to use that smaller number. It's opening up 30 degrees, and I've actually just answered one of my questions here. The measure of angle AOC is equal to 30 degrees, and we can just take that number right off the protractor because the other ray making up that angle goes through 0 degrees. If OP is, and I'm going to have a P up here, but we're going to just use different letters. If OP is paired with X and OQ with Y, then the measure of angle POQ is equal to the absolute value of X minus Y. What the heck does that mean? Well, back with our protractor, if you're able to put one ray right through 0, then you can look at the other ray and just identify the angle mark and go, okay, that's 30 degrees, and I just wrote 30. But if we look at the measure of angle COD, okay, so COD, I've got kind of a complex diagram here with a bunch of angles going on or emanating from the same vertex, and I don't want to just move the protractor all the time. Maybe, and you can if you're just doing simple numerical measurements, but we're going to ultimately move into doing some problems that involve a little bit of algebra, and with those more complex questions, you need to understand how to find measurements of angles without constantly moving that protractor around. And so let's get to it. We have COD. So we're going to have this 30 and this 45. So if I want the measurement of COD, what I'm going to do is I'm going to take the absolute value, and that is to prevent us from having a negative angle measurement. Think of a tape measure, you know, those like that sort of metal, usually metal or plastic box, and you pull the tape out. You can only measure positively. That tape measure doesn't start whipping inside and somehow come up with some magical negative measurement. If you're measuring height, weight, number of degrees that an angle opens up, there's only positive measurements, and the absolute value is going to make sure of that. But I don't think I left myself enough room here. So we're going to take the 30 and the 45. That would represent sort of our x and y that's in part B of this postulate, and subtract them, except I wrote 40. Well, 30 minus 45 is negative 15. Well, if I had done 45 minus 30, of course I would have gotten that positive angle measurement that we needed. But just in case we do the subtraction in such a way that gives us a negative number, the absolute value will make sure to say, okay, let's not forget measurements must be positive, and angle, the measure of angle COD, or DOC, is 15 degrees, and such. Therefore, what is the measurement of angle DOE? Starting here, D is going through the, I'll see this 45 degree mark on my protractor, and I've got another angle going through, again the vertex here at O, going through 120. What is that again? Let's see. It's going to be the absolute value of 120 minus 45. Well, 120 minus 40 is 80, and 80 minus 5, doing that in 2 steps in my head, is going to be equal to 75 degrees, so the final answer is 75. So that is how you, with a diagram now, understand what the postulate theorem, or the postulate, the protractor postulate is actually trying to say, and a little bit of how you use that protractor when you get one in your hands and you're working with your homework. Let's get to the next topic, which is going to be, I don't know, we'll figure out when we come back. Let's talk about the angle addition postulate. If point B lies in the interior of angle AOC, then the measure of angle AOB, so we have AOB, keeping that vertex in the as a center variable, plus the measure of angle BOC, then the sum of those two parts, what kind of makes sense, is going to equal the measure of the interior, or the entire angle, AOC. So AOB, this bottom section, plus BOC, the measure of angle BOC, this top angle, when you add these two together, you should get the measure of the entire, sort of these two parts are on the part of this outside angle of AOC. And you can see that my face is getting a little orange and a little dark with the clouds coming in, so let me fix that. Okay, hopefully that's a little better. And that would make sense, right? If an angle opens up 10 degrees and then opens up another 30 degrees, my hand motions are way too big there, but if you open up 10 and 40 degrees, you're open up a total of 50 degrees, right? That kind of makes sense. Here's what it's going to look like with a little bit of algebra. Got to keep those skills fresh from possibly last year, to know where you're going to school at, but that's always important. We're still going to be mixing up some algebra with our geometry. So if the measure of the angle AOC, the entire angle around the outside, if that measurement equals 74 degrees, then let's go ahead and solve for x. Okay, so this entire angle around the outside here has a measurement of 74 degrees, and we have two unknown parts of 3x minus 10 and x plus 7. Well, the angle addition postulate simply says add them up and make it equal to 74. So we have 3x minus 10 plus x plus 7 is equal to 74 degrees. I'm not going to keep writing that little 0 there, but until the end, but it is 74 degrees. And actually, never mind. Yes, I will. I'm only including these parentheses here to do a couple of things. I want to highlight the fact that I'm just simply adding the measurement of two angles, and it's always a good idea to use parentheses when you do substitution anyway. Like say if we were subtracting the measurements of the angles for some reason, we would want to remember to distribute that negative sign through the parentheses. Okay, so we're just doing addition. There's nothing in front of these parentheses, no exponents, no fraction bars. So we're kind of just there to emphasize the two angles. We're going to add like terms. So we have 3x plus 1x. So 3x plus 1x, we're going to add the coefficients. 3 and 1 is equal to 4. So we have 4x and negative 10 plus 7. negative 10 plus 7 or 7 minus 10 is going to be equal to negative 3, and that's equal to 74 degrees. We're going to go ahead and add 3 to both sides, so we have 4x, adding that 3 to both sides, we negative 3 plus 3 is equal to 0, and 74 plus 3 is equal to 77. And I'm going to kind of drop the degree symbol at this point, because when we get done, I don't want you to think of x as being the size of either one of these angles, the measurement of the degrees of either one of those angles, because x is going to have to be plugged back into these expressions to find the measurement of angle COB and find the measurement of angle BOA. I didn't set this example up to find those two measurements, but that's what you would do. We're going to divide both sides by 4 and get x is equal to 77 over 4. And if you want to write that in a mixed fraction form, you'll do 77 divided by 4, and that will give you 19. And 19 times 4 is 76, so you'd have a remainder of 1. So this becomes a mixed fraction of 19 and 1/4. Just want to make sure that I'm giving you the right answer. Now this is just the unknown variable of x. If you do want to or need to, because of your directions, find the measurement of each of those two angles, you will need to take x and plug it into the expression 3 times 77 over 4 minus 10 to get the actual angle measurement, the number of degrees, and of course the same for the bottom angle here as well. The second part to the angle addition postulate is just a special case. In case you happen to read a problem that says that the angle is a straight angle. You're going to have to, in geometry, as well as any other math class, really work on knowing your vocab and learning these postulates and what they say off the top of your head. So if a problem says that an angle is a straight angle, you need to know that that means it's 180 degrees, that it opens up and has a full 180 degrees. You'll be kind of effectively looking at a straight line. If you don't know that, you'll have some questions you won't be able to do. So if angle AOC, see how it looks like it's a straight line, is a straight angle, and B is any point not on AC, and the ABC thing is for the definitions. These can be identified as with any variables you like, or your textbook may like to use. But then the measure of angle AOB, so AOB, plus the measure of BOC, keeping those vertexes in the center there, is equal to 180 degrees, because a straight angle is an angle who's opened up a full 180 degrees. Given that AOC is a straight angle, solve for x. Now here in yellow, with these expressions in here, that's all your textbook should have to tell you to set it up for you to solve for x. They don't have to tell you that the angle is 180 degrees when they tell you it's a straight angle. That's for you to know. So we have we have these angles. We're going to define adjacent angles here in a second. We have these adjacent angles. They are coming together to add up to this full angle of AOC. So the angle addition postulate says, take this first part, add it with the second part, and make sure that equals 180 degrees. And this now will finish just like this problem did over here. X and 5x is equal to 6x, minus 10 is 180. We're going to add 10 to both sides of the equation. Whenever you want to move a number, or a variable for that matter, from one side of an equation to the other, you want to always do the opposite math operation. And so that's going to be 6x is equal to 190, and divide both sides by 6, and we get, let's see here, I'll just cheat, 63 and a third. Wait a minute. Yeah. No, this can't be right. Found a little mistake in my notes there. Okay, so we got to 190 over 6. That reduces to 95 over 3. These both have a divisor of 2. And then if you want to make that improper fraction into a mixed fraction, I think I called it a compound fraction over here, so about that. So if you want to convert that to a mixed fraction, 95 divided by 3 is 31 point da 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 da. So there's decimal afterwards. So 31 times 3 is equal to 93. Okay, 31 times 3 is equal to 93, and 93 from 95 gives a remainder of 2. So we have 31 2/3. So that is the angle addition postulate. Let's define what congruent angles are, adjacent angles are, and define an angle bisector. And this video will be done, and hopefully this lecture will help you get your homework finished. Thank you for watching. Here we go, last screen. Congruent angles have equal measurements. So we have an angle here drawn, I just identified it with one letter, and angle DCB. Those angles, if given, angle A is congruent to angle DCB. Well, if that's the case, then if you're told that they're congruent, then you can say that the measure of angle A is equal to the measure of angle DCB. Another thing to be aware of is when you look at your math diagrams, if you have some angles drawn like this, and I could tell you that these angles are congruent, or with a symbol I can draw some arcs through here. In geometry, we're going to use those little arcs we put through the corners of the angles as equal signs. So if I do this in my diagram, I am indicating that those two angles are equal in measurement, and thus they will also be congruent. Please note the congruent symbol, the equal sign. We talk about measurements, the M here, measurements being equal. Okay, so it's not the same to say that two angles are congruent. It's not the same as saying that their measurements are equal. It's a definition, goes back and forth, but it's not the same notation. Adjacent angles are two angles in a plane that have a common vertex and a common side, but not common interior points. So I have four diagrams here that could identify or be angles that are adjacent. So which ones are and are not? Well, with our first one here, we have angle 1 and angle 2, the yellow and blue one. We have a common vertex, and they are, of course, sharing the entire this entire side, this entire ray, which I don't have any letters to name it, but we do have a common vertex and a common ray shared between angle 1 and 2. So these are adjacent. In this diagram, we have two angles, angle 1 and angle 2, sharing a common vertex, but you can see that angle 1 is made up of these two yellow rays, and angle 2 is made up of these two blue rays, and nothing else is in common except for that vertex, so those are not adjacent. We have angle 1 and angle 2 sharing a common ray partially. Angle 2 shares most of this ray, but not all of it. See, they don't have the same vertex, so these are not going to be adjacent angles. And over here we have a common side. That's good. We have a common vertex being shared between angle 1 and angle 2. Now if I look at here and I look at here, you might be going, well, so let's just put another arc through here. I'm just really trying to identify how far angle 1 opens up, that it goes from this side to this side, and I'm not trying to identify those being equal, so let me change that a little bit. So we have a common side and a common vertex, but you can see that angle 2 is within angle 1, so they're sharing some interior points. So this is also an example of two angles which are not adjacent. Our last definition, angle bisector, or a bisector of an angle, is a ray that divides the angle, and we're talking about, ultimately we're going to be talking about here of angle DEF, into two congruent adjacent angles. So all I have here though is, from my diagram, you can assume that all points are coplanar, that I'm talking about D, H, F, and E. They're all on the chalkboard, so they're all coplanar. You can see that ray ED and ray EH and ray EF all intersect. They also all have the common endpoint or initial point of E. And you can see that angle DEH and angle HEF are adjacent. They share this angle here, DEH, and HEF share that vertex and that common side, so that they're adjacent. But you cannot assume that these angles are congruent without some marks in here. So if this were your diagram in your textbook, you could not look at that and assume these two angles are equal. But you can. You're not assuming that they're equal, you're concluding or being given that those angles are equal if you have those little arcs in the angle measurements. And if there's a bunch of angles, you might see, you know, 2 arcs or 3 arcs, but those angles that have the same number of these little arcs in the corners, that's your textbook telling you that those are equal. So what do I want to do with this? Well, let's see here. I just want to make sure I don't miss something from that I want to include. We have angle DEH is congruent to HEF. That means that they're, let's see here, angle DEH is congruent to measure angle HEF. That now, of course, also means that their measurements are equal. And let's see, let's pick on this angle here, HEF. The measure of angle HEF, and I want to compare that to the measurement of the entire angle, the outside angle, DEF. Oh, got my little angle symbol there. DEF is the entire angle, right? And it's been bisected or cut in half. So if I just look at HEF, which is half of the entire angle, then I can say that twice the measurement of this small part, it takes 2 of these halves to equal the measurement of the entire angle that was initially bisected or cut in half. I could also say that the measure of HEF is equal to 1/2 the measure of the original angle DEF that was then bisected by ray EH. Well, that is the end of my introduction to angles and many, many definitions included in the video. I hope you appreciate the fact I'm wrapping all these up and not making you click through a bunch of small little videos and give you one, nice, concise, complete lecture to help you get your homework done. So, now I'm done. That means it's time for you to go do your homework. Bam!